So hi everyone, welcome to the afternoon session, and we begin with a talk by Albachiara Cogo from Tübingen on uniqueness of photon spheres. Please welcome to the screen.
Good afternoon. Can you hear me?
Yes.
Okay, perfect. So thank you for the opportunity of speaking here. I'm going to talk about my master thesis work, which was done under the supervision of Karls and Lorenzo Mazzieri, and it's about the theorem of uniqueness of photon spheres and more generally of equipotential photon surfaces in geometrostatic spacetime. And I'm going to prove it the potential theory. So let's state immediately our goal. The theorem says, roughly speaking, that if we have a geometrostatic spacetime, four-dimensional, L4G, and if we have a connected photon sphere embedded, or more generally an equipotential photon surface embedded, then the geometrostatic spacetime must be isometric to the Schwarzschild spacetime. Okay, this theorem has actually already been proven multiple times, always adapting the black hole uniqueness proofs. So the black hole uniqueness theorem is almost the same statement, replacing photon sphere with black hole horizon. And so these adaptations were made by Cederbaum, Fehrenbach, Cederbaum and Galloway, adapting the proofs of Israel, Robinson, and Banti Masudul Alam. And what we have tried to do is to consider the potential theory developed by Agostiniani and Mazzieri and apply it to our photon sphere uniqueness. So let's fix the notation. A geometrostatic spacetime, which is our ambient, it's an n+1 dimensional spacetime, such that it's standard static, which means that it's a warp product just of R and a Riemannian manifold Mg, and with warp function n, which is called lapse function. And then it's asymptotically flat, which means that this Riemannian manifold at infinity behaves like a Euclidean space. And then it is vacuum, which means that the Einstein vacuum equation is satisfied. And so the Ricci of this spacetime vanishes. And clearly the triple given by the Riemannian manifold and the lapse function, which is called static system, uniquely identifies this spacetime. And I'm going to use the static Einstein equation then, which actually corresponds to the Einstein equation, but written only in terms of this Riemannian manifold and this lapse function. Okay, so a specific example of geometrostatic spacetime is given by the Schwarzschild solution. Here I've just written it down to fix the notation again in Schwarzschild coordinates. So it is in fact the work product between R and this Riemannian manifold with this Riemannian metric, and the lapse function is given by this function, and it's also involved in the Riemannian metric. Okay, now let's introduce the definition of photon surfaces and photon spheres. So a photon surface is an embedded hypersurface in our spacetime, such that it is timelike. I hope it's clear in this picture. Namely, the induced metric is still Lorentzian. And then it is null totally geodesic, which trivially means that every null geodesic that at some point is tangent to it remains tangent to it. And this corresponds to being totally umbilic inside our spacetime, and to have a physical intuition of it, it means that light, so photons, which trajectories are identified by null geodesics, are trapped into these surfaces. Okay, and a specific case of photon surface is given by the equipotential one, which means that if we consider this sigma surface and -1 dimensional, which is given by the intersection of the photon sphere and the Riemannian manifold Mg, which foliates the spacetime at some fixed time t, then okay, in the picture is represented by this red line. Okay, so this sigma here is such that the lapse function is constant on each connected component of it. And if the lapse function is constant regardless of the time we are fixing, so actually on the whole photon sphere, or better in every connected component of it, then we have a photon sphere. Okay, and here I just draw the photon sphere in Schwarzschild to give an intuition. So the photon sphere in the Schwarzschild in 3 dimensions occurs at r equal 3m in Schwarzschild coordinates, and it's slightly above the black hole horizon, which occurs at r equal to m. And in the whole space-time, it can be imagined as a cylinder where, okay, the light is trapped. Okay, so finally, I'm going to talk briefly about potential theory, which is the tool that I'm going to use to prove the uniqueness. So this theory just takes Riemannian manifold mg0 and a smooth function n, such that the Riemannian manifold is asymptotically flat, and this triple satisfies these conditions. The first two ones are the PDEs that corresponds to the Einstein equation, and they are the static Einstein equations, and they are actually written in terms of the Riemannian manifold. So the tensors of the Riemannian manifold and connection of the Riemannian manifold, and the Laplace Beltrami operator of the Riemannian manifold, and the lapse function, which more generally is called static potential. And then we want this smooth function n to, we just take it such that at the boundary of m attains this value n0 between 0 and 1. And at infinity behaves like this. So it goes to 1. And the first approximation is given by this m, which is called mass parameter, and actually corresponds to the ADM-mass of this system. Okay, so in this setup, Agostiniani and Mazzieri in their potential theory papers just started from this function, which is u1, which is a function of s that goes from n0 to 1 and identifies the level sets of n across our Riemannian manifold mg. And it's given by the integral of over a level set of the norm of the gradient of n. And clearly, since by the second static Einstein equation, our n is harmonic, this function is constant, so it doesn't depend on the level set we are considering, and it holds for any static system. And it actually has this value, which is the value at infinity, and involves the mass parameter and the volume of the n-1 dimensional sphere. So they started from this observation, and they generalized this idea to any p bigger or equal than 1, taking these UP functions, which are given again by a function and an integral over a level set of the norm of the gradient of n to the power p. So in this case, apart from the case p equal 1, at infinity, we still have this behavior, this value, as a limit, involving again the mass parameter and the volume of the n-1 sphere, but they are a priori not constant on each level set. It only happens in the Schwarzschild spacetime. So somehow these functions can be used to detect whether we are dealing with Schwarzschild or not. And in fact, this is written rigorously in this theorem, which says that for p slightly less, for every p slightly bigger than this optimal value, which is slightly less than 2, our UP functions are differentiable, and the derivative is always non-positive, which means that the UP functions are non-increasing somehow along the level sets of n, and also this let's see that this derivative involves again an integral over a level set of an integrand function that involves the norm of the gradient of n and the mean curvature of our level set. And in the rigidity case, so if this derivative is 0 at some level set, which must not be the 0 one, because otherwise this is trivially 0. so it doesn't give any information. So if it's in the rigidity case, we have it implies that we have the isometry to the Schwarzschild solution. So in order to apply this, we want to apply this theorem for our uniqueness result, and so we want to prove that having a photon sphere, or more generally an equipotential photon surface, we actually are in the rigidity case. So let's observe that to be in the rigidity case. So here to have equals 0, we just have to impose that this integrand is less or equal than 0, because here we have a minus some positive quantity. And this is true. I mean, a sufficient condition for that is just that this inequality holds almost everywhere, which means that the quantity in the brackets here is less or equal than 0 almost everywhere with respect to the Austin measure on some level set of n. So now the easiest way to try to prove it is just to take the value of the lapse function on our equipotential photon surface at some time and see if it's satisfied, and then we can conclude. And in fact, using the properties of equipotential photon surfaces, which are the following, we are able to rewrite this sufficient condition in a very easy way, just imposing a lower bound on the lapse function, on the value of the lapse function on the equipotential photon surface. So these equipotential photon surfaces are such that if we consider their intersection at a time slice, okay, this sigma, the resulting sigma, is such that it has a constant mean curvature inside the Riemannian manifold, and also the normal derivative of the lapse function with respect to the outward normal in this Riemannian manifold is also constant, and it's related to this constant value of the mean curvature h and the value of the lapse function, which is also constant again on the equipotential photon surface, via this identity, which involves a parameter c. This parameter c actually identifies somehow the type of equipotential photon surface that we are considering. And in dimension 3, if it's equal to 3/2, we have a photon sphere, which is just a specific case of it. And then finally, we have also that the scalar curvature is constant, and it's related to the mean curvature by this identity. So we are going to use these identities to rewrite the previous sufficient condition to be in the rigidity case, and it gives just this inequality, so this lower bound for n0. And in dimension 3, it corresponds to this right-hand side 1/√2c, and of course in photon spheres it's just 1/√3, which is in fact the value of the lapse function on the Schwarzschild photon sphere that I drew before, that we have seen before, yes. So, okay, we are only left to prove this lower bound for n0 to conclude, and we can still use potential theory and observe that since the UP functions are non-increasing along the level sets of n, the UP functions computed at n0 have a bigger value than the value at infinity. And this rewritten in terms of the property of equipotential photon surfaces and playing with this inequality somehow, we get this lower bound for n0 with which involve this b, and b is this quantity here, which is written in terms of constants and this parameter c, and but more precisely in terms of this integral over a level set of the scalar curvature. So somehow to have a precise bound here, we need to bound the integral of the scalar curvature. And this is possible, of course, in dimension 3 using Gauss-Bonnet, since it's possible to prove that actually the photon sphere is actually a topological sphere. Okay, so we can still use Gauss-Bonnet and find an upper bound for this integral and actually get what we wanted and conclude. But okay, we have to work first of all in dimension 3, because in higher dimension we have no analogous to the Gauss-Bonnet theorem, and also we have to impose that this level set, so the equipotential photon surface, has only one connected component. And because if we assume, for example, a k is the number of connected components that we assume at the beginning, for example, then we get this bound on the right hand, this value on the right hand side, still using Gauss-Bonnet under some assumptions. And this is strictly less than the value that we want to attain, so we cannot conclude. And okay, and these two observations are what I'm going to point out at the end, because okay, as I said at the beginning, there were other proofs of this theorem, and in fact, the Banting-Masoudou-Lalame and the Zederbaum and Galloway adaptation didn't assume the photon sphere to be connected, or the equipotential photon surface to be connected, which was the case in this proof. But it also, I mean, it was a good way to prove it somehow, because we avoided the assumption of regular foliation by hand, which is a big deal somehow. And also we avoided to use the positive mass theorem, which was used by them, and it's a very strong result somehow. Okay, so these are my references, main references, and thank you for your attention. I'm here for any questions.
Thank you for your talk. So it's time for questions.
Piotr, may I ask a simple question related to the definitions? Because I missed something about this photon sphere. So there was this photon surface. It is of codimension 2 or for codimension 1? This is crucial, yes? So on this picture, this is the hypersurface of codimension 1, yes?
The pink one, yes.
Yes. And then,
yeah.
And then you assume that this is not totally geodesic, but null totally geodesic, yes, which is less than totally geodesic. So this means that the part of the extrinsic curvature vanishes. Which part of the extrinsic curvature vanishes?
So
for null totally geodesic.
So it can be proven that it's this being null totally geodesic is equivalent to be totally umbilic. So
because
somehow
totally geodesic surface means that the full extrinsic curvature vanishes, that the geodesic internally and the geodesic in the ambient space is the same geodesic. But here maybe you assume that when you start with a null, so in some sense on this surface there should be null directions, yes? It cannot be space-like. This free space in classical 4 dimensions. So
it is time-like. So
I try to recognize because there is another surface which is better known is how do you say it in English? Non-expanding horizon, yes, and then the full extrinsic curvature vanishes, and this is null surface. So I try to understand this hypersurface. What is the signature of the metric?
No, so the signature is it's a Lorentzian metric on the surface. It's not null.
Okay.
Because it's the first condition.
So this is time-like, yes?
Yes, it's time-like.
Okay.
This is the first condition. And then if we consider, taking a null geodesic in the ambient space, then it's also a geodesic in our photon surface.
Okay, so okay, I understand this definition, but can you transfer this definition to the extrinsic curvature condition? This is my question. That some component, maybe this null component of extrinsic curvature vanishes, or something like that.
So you mean the mean? So okay. Yes.
So the full tensor. So roughly the derivative of this Lorentzian metric in transverse direction to the surface.
So you mean the second fundamental form?
Extrinsic curvature.
Yeah, the second fundamental form.
Yes.
You are asking. Yes. So the second fundamental form is pure trace. So it can be written as the mean curvature over the dimension of the hypersurface, so over n, times the induced metric. And actually, yes, it's positive, the mean curvature.
So this is so the extrinsic curvature is proportional to the metric?
Yes.
Okay.
Yes. I mean, I can give you also the reference of this proof, but it's actually, stating that it's timelike and not that geodesic is equivalent to say that it's totally umbilic. So the second fundamental form of the extrinsic curvature, it depends on the name you give it to it, is a multiple of the metric. Yes.
Okay. Thank you very much. Okay.
Okay. So we still have time for one question.
If I may, can you hear me?
Sure.
Okay. Yes. So you mentioned that your proof has some advantages over the other ones because you're making less assumptions somewhere. So what would be the optimal statement then?
Without one connected component, because the optimal statement is removing this connectiveness. And in fact, Sederbaum and Galloway did it, but they had to use the positive mass theorem. I didn't use it.
So if you remove it, you get a clean statement. There's no need to. There is no. I mean, it's a nice technique what you've done, so it's very interesting. But so they already have the optimal theorem now for this problem.
Yes. In fact, at the beginning, yes. Actually, yes. And also they proved it in higher dimensions. But okay, somehow we tried to see if with this technique maybe it was possible to. And,
yes, of course, it's always interesting to have new proofs.
Because it was really a technique which was really topological and somehow using very strong other strong theorems. Yes.
Okay.
Thank you very much.
Thank you very much for your talk. So it's time for the next talk. The next talk is by Leo Bigorn